from Professor Samir Shende. He presented a great tutorial yesterday, as some of you were there. Huh? No, this is some new people. I'll quickly. So he has developed the Tau performance system, the program database toolkit, and the extreme scale scientific software stack, which is E4S, and the HPC Linux distro. His research interests include tools and techniques for performance instrumentation, measurement analysis, runtimes, etc. He serves as the research professor and the director of performance research lab at the University of Oregon.
Thank you.
So he'll be today talking about Tau performance systems. Yes.
Great. No cable connected? Connect your device. There. Can you? I thought it's not connecting to this. Nat needs to fix that over there.
The refresh zone.
Should I bring my laptop? Okay, good.
Okay.
Okay, great.
Go to the main page. Yeah.
Okay. So I would like to thank the team at the Ohio State University, the MVAPICH team, and the Tau team at the University of Oregon. The key problem that I'm trying to address here is that it's getting harder and harder to measure the performance of our applications in HPC and AI/ML space because the hardware complexity is rising. And it's even harder to install our tools in a consistent manner. So our goal here is to create a toolkit that will make your life easier to understand the performance of your complex codes. And the Tau performance system is a toolkit that's been in development for over 25 years. And it's a comprehensive profiling and tracing toolkit that easily integrates with your applications. It can show you where your application is spending its time. It's open source, BSD style licensed, and it uses performance and control variables to interface with MVAPICH. It is supporting many different runtimes, MPI, CUDA, ROCm, DPC++, OpenCL, OpenMP. It supports different languages, hardware performance counter, libraries. It supports timing libraries that have been integrated in your numerical libraries, like PETC has perf stubs integration. So when PETC has timer calls for start and stop, they ripple into the Tau timer calls. And so you can see detailed information about packages from PETC or XGC using CAM timers or the COCOS profiling API, MPI, and other systems. The key takeaway from this talk should be that there is no need to change your source code. There is no need to change your build systems. There is no need to change your binary. You simply launch it with a tool called Tau exec, and then it will generate the profile files, the trace files, and you'll be able to analyze the data. It also supports some new platforms over here. There are a number of tools for analysis, and here is our website. So in case you are wondering, what can it show you? It can show you where the application is spending its time, in which code regions. These could be functions, these could be basic blocks, loops. It could be kernels running on GPUs, OpenMP loops. It can show you instructions instead of time. It can show you hardware performance counter data from PAPI and Liquid instead of wall clock time, or in addition to that, and more importantly, it can show you how much time your application spent waiting at a barrier inside a collective operation and where that collective operation took place in your code. If you see a timer called MPI collective sync, it means this is the time that was wasted, just plain out wasted in a barrier because it was stuck. It was stuck waiting for other processes to reach that barrier. It can show you memory information, even the high water mark, the energy usage, I/O, and how your application scales. This is just a quick start guide that shows you can just launch the code with tau exec. You can set some environment variables to generate trace files, merge and convert trace files, and analyze the data. There are many ways of injecting hooks into your code. I mentioned that you can use unmodified binaries, but if you want to go deeper, you can instrument the source code, use wrapper interposition libraries, you can add hooks during linking, even rewrite binaries. And yes, you can take an unmodified binary, tau can read it and inject the hooks and rewrite it so that you can then analyze the application with function level entry exit hooks. Once these hooks are inserted, you can then have different measurements that are made using profiling and tracing and generate the data and analyze it using the visualizers. So you can see here there are a number of instrumentation options for different languages, runtimes, and analysis tools. Here is an example of just performance data generated with tau, where you can see event-based sampling and how OpenMP can be used to instrument the OpenMP code using OpenMP tools interface and comparing different MPI ranks with tau's visualizer. Here are examples of tau being used with the MPI collective sync. You can see that there's 14 seconds wasted in the MPI barrier, and you can see which MPI collective operation was responsible for that call. Here, in this case, you can see that 8.1 seconds out of the 14 seconds came from MPI reduce operation. And then you can go down and see every location in the code. Here is an example of time wasted in a pthread condition wait. Tau has event-based sampling. It can easily detect the time spent in such wait calls, and you can then diagnose the problem. The key thing to remember is that you need to add hooks to your code. This can be done in many different ways. You can add hooks in the source code with the compiler, even runtime preloading, where you just use the tau exec tool and you don't need to modify anything else. There are many different runtimes that we support, including MPI, where we support the MPI PMPI interface as well as the MPI tools interface, and we can show you the time spent in the collective sync operations. pthread, OpenMP, where OpenMP tools interface is supported, Intel level 0, DPC++ SYCL support, OpenACC instrumentation. We have support for OpenCL, CUDA, ROCm, Cocos, Python, and the best part is you can mix and match these runtimes. So if your application is using MPI with CUDA, you can configure tau with support for CUDA, and it will use the CUDA profiling tools interface along with the MPI profiling interface and show you the full breakdown of runtime with no change to your application. We also have introduced support for rewriting libraries. You can rewrite a binary using Dynenst API, and it will add hooks at the function boundaries. But now, if your application was complex and you didn't want to instrument the whole application, if you said, I am only interested in instrumenting the HDF file library, say, then you could pick the library and rewrite that binary for the library in a different directory, set the load library path, and run the application unmodified with the rewritten binary. So you will be able to see the entry-exit instrumentation that comes from that library. So there's a -L option for the tau run command now that allows you to rewrite the binary. Here is an example of using tau with a dynenst equals download, where we take care of installing the dynenst API package completely and then building it so that you can use it with the rest of your runtimes. Here we have an example with MPI and ROCm with Rock Profiler. And to show you an example, here is a profile file where I have just said with a filter file that I am only interested in HDF5 and only use instrumentation in H5 star. Any function that starts with capital H5, please instrument it. The rest of them, ignore them. So you can see all the H5 functions instrumented by rewriting the library. Here is an example of the AWP ODC code from University of California, San Diego, SDSC. And in this case, we have rewritten the binary as well as we are using ROCm. So with this, you can see MPI calls, you can see the calls in the application, and then you can see the actual kernels running on the GPU. These kernels are spawned by AWP ODC, and you can see the dtopo kernel functions that are created by this application. So you can have a combination of instrumentation approaches. You can rewrite a binary, you can rewrite a library, you can just use event-based sampling along with MPI instrumentation. You can use ROCm instrumentation to instrument all the kernels running on the GPU. So the key takeaway is you can use tau exec and then enable other options like event-based sampling or other communication. If you are using GPUs, we have support for kubectl, for CUDA. You have support for level 0 for Intel GPUs, OpenCL, OpenACC, and ROCm for AMD GPUs. You can look at the I/O in your application by saying tau exec-IO, enable OpenMP tools interface with the -OMPT. You can even run the memory debug for bounds checking. If your application is exceeding the allocated bounds, you can do bounds checking. You can use memory leak detection. You can use event-based sampling, even with hardware performance counters. With this tau exec tool, you can do a lot. You can instrument in different runtimes and generate the performance data. It generates profiles as well as traces. Profiles show you the cumulative summary statistics, while traces can show you along a timeline what happens when. Yesterday in our tutorial, we were looking at trace files generated by tau as well as profiles. With instrumentation at the entry and exit, you can see the inclusive time in a function as well as exclusive time in a function. Exclusive is the time spent in, say, foo, outside of the time spent in bar. And then you can generate different flavors of profile files, like a flat profile, a call site profile, a call path profile, all the way to a trace file. Now, what are these? Call path profiles can show you the time spent along a calling path, an edge in a call graph, where you can then set these environment variables to generate the time spent in MPI send when it was called by F2, when F2 was called by F1, when F1 was called by main. You can see the time spent at a given source location. So I could say the time spent in MPI send at line number 12 in foo.c was so much. You can generate phase profiles that are flat profiles nested under a particular phase. And you have the support for start-stop instrumentation, which can give you fine-grained control, as well as sampling, where you can periodically interrupt the program. Sampling works like this, where you can interrupt the program periodically and then make an estimate for where the application is spending its time, whereas instrumentation allows you to add hooks with start and stop timers inside all the functions. Here is an inclusive profile. The top level timer is .tau application. It just is the timer that starts with the first event in a thread and ends with the last one. And here is an example of a loop level profile. We are seeing the exclusive time spent in different code regions. So you can pinpoint and say, in that particular point solve 5 point solver loop, from this line to that line, I'm spending the most time in this computational fluid dynamics code. This is a timeline view where you can see a timeline and all the processes and what each of them is doing. And there are boxes within boxes in this jump shot trace visualizer, which ships with tau. This is a trace visualizer that was built at Argonne National Labs, and they have allowed us to redistribute jump shot with tau. You can also use Chrome trace browser. Yes, every Chrome browser comes with a built-in trace visualizer, but they have moved to a more state-of-the-art trace visualizer, and Google has created perfecto.dev. This website can allow you to upload the traces generated by tau, so you can see the activity with a flame graph that shows you the levels of nesting, the calling from main to the simulation to propagate and so on. And so along a timeline view, you can see what every thread is doing. This data is generated by tau with the entry and exit instrumentation. So if you instrumented your code using Dynenst API, you will be able to generate such detailed trace files and see the time. This is the commercial trace visualizer called Vampire. It comes from TU Dresden in Germany, and it can be used with tau using the open trace format OTF2 traces. The advantage of this visualizer is that there is no need to merge and convert traces, which can be an expensive operation as you scale up your application. As soon as you complete the execution of your code, you can launch Vampire and visualize the OTF2 traces. On the con side, you have to pay for this. The other visualizers are free. Okay? So this saves you time. So it depends on your priorities. We have Paraprof, which is a profile browser that comes with tau. You can launch it and you can see what each rank is doing. Note that the color represents a function or a code region and the cumulative time spent in that. This is a profile file, not a trace. So the time represents the total time spent in it. And we have a 3D profile browser. This is Paraprof, where you can see the MPI ranks, you can see the functions, and the height and color can be adjusted by the drop-down menus over there. What this allows you to do is it shows you the shape of the full profile. You can see what one function was doing with respect to another. You can see in this figure, one is having a concave shape, the other is having a convex shape. They add up together to a constant. So this view in 3D can show you a lot about your code as you navigate the space. And then you can have the crosshairs that can show you where they intersect, what is the height and color value. So you can see, instead of trying to click in the 3D space, you can just use the function and thread sliders over there. We also have 3D visualization with communication matrix displays, which can be very useful for those who are investigating the MPI performance. You can see the senders and receivers, and where they intersect, you can see the values that you pick from height and color. These can be max message size, message volume, bandwidth, and so on. So all I need to do is launch an application, say a.out, with tau exec -event-based sampling, EBS, and then it will show me that at this line, how all the ranks were performing. Some code region where it's taking time. So you can see on a thread by thread, rank by rank basis, how your application was spending its time. With MPI, we have the integration with the MPI tools interface, where we have, with MVAPage in particular, the MPI T interface, which allows you to create a bridge between the performance evaluation tool and the runtime that can exchange information. You can see low-level performance variables that are inside the runtime, and this is exposed through the bridge MPI-T. Tau also has support for a plugin architecture, and you can use both the MPI-T in a non-interactive mode, a user interactive mode, and a policy-driven mode to change some key parameters for the MPI runtime. And with this model where we have a plugin, you can then use this to extract information about entry and exit and key events that take place, and then provide that to the plugin like this. So you can have a plugin observe the events that take place in Tau, and then it can perform actions. So you don't have to write your new tool from a scratch. You could just create a Tau plugin and access all the information about GPU runtimes, MPI, I/O, and memory events. So you could create a new tool very easily using this plugin architecture, and then interface with your application. And you can have multiple plugins as well. So to show you an example of how this would work, this is a plugin that checks for the performance and then creates recommendations. These recommendations, such as this Tau recommendation of phase, on a phase-by-phase basis, is saying, please use the sharp interface because you're spending too much time in a collective operation. Offload that operation to the sharp interface and let the smart NIC take care of the collective operation. So there are a number of different memory related internal control variables. You can think of these as knobs. Your application is running. You can turn these knobs at runtime and then affect the behavior of the MPI runtime. And MVAPage provides a large number of these control variables that the plugin can internally change, or you can specify control variables with even environment variables. So you can do that with an environment variable which is like this. Here I'm saying track the performance variables from MPI tools interface. These are the control variable metrics, and these are the values. And then I just launch the uninstrumented binary with Tau exec, and then it can make those changes. And here is a complete listing of the performance variables that are collected in a run, the control variables that you can use, and there is detailed information for each control variable that you can set with environment variables like that. And then setting these variables, they can be arrays as well and have multiple variables specified with running your application and analyzing the data. Here is an example of the performance variables that you are seeing with the VBuffs, the memory buffers inside the MPI. And you can then change the values so that you reduce the amount of VBuffs that are available. For example, if you start up by default and MPI is taking up a lot of memory and you need that memory in the application, you could dial down the number of VBuff pools and it will use less memory internally, and then your application could in turn use more memory. And here are some examples that show the usage without the CVAR and then with the CVAR where the performance is changed. We also have support for per communicator based variables where you can specify the communicator This is the same communicator name that you can set with MPI com set name, and then you can specify that communicator. If you say, my application has odd and even ranks, and I'm going to have separate communicators called odd and even, then I can set a control variable for just the odd ranks, for example. And here are examples for tuning this with the comb application. And you can see the profiles. I don't want to go into details. These are just available to show you how the control variables can be used. We also have support in Tau for tracking the path that a message takes in a multi-GPU system. Our systems are getting complex. Your communication, which goes from one GPU memory to another GPU memory across different nodes, may follow a path that goes from GPU A to GPU B to GPU C, going via RDMA to the other node, and then again hopping through multiple GPUs to finally rest in the destination GPU's memory. That path that the message takes can be charted out using Tau with the help of the information that's provided by MVAPitch. And here are examples of the path IDs where you can see the time spent in that path. Now, I had mentioned that you can see the collective sync time, which is the time spent in a barrier operation inside a collective. I run this code and it shows me that 574 seconds were wasted in an MPI barrier within a collective operation. With a call path profile, I can now see that out of the 574, 382 seconds came from MPI all reduce. So then I can look at the MPI all reduce and then see where it's getting called and then identify that. In other areas, these are CAM timers which the user had put into their application. And those timers automatically show up in Tau profile data, as do COCOS timers. In COCOS, which is a C++ runtime for the node level programming, you can specify the first argument of a parallel for, parallel scan operation with a character string. In this case, the user has used a string called set buffer particles _d. This means a lot to the user. That first argument shows up in Tau profiles where it shows you the parallel for timings. You can look at these things where the collective sync operation, it shows you the names of the timers used internally in the application. So you can see that when total called init, when it called iSetup, iLoad, MPI all reduce, the time spent in the collective sync operation is so much versus the other location of collective sync where it was called from the reduce to. So you can just see the call path and identify where the performance was lost by the time spent in barrier calls. There are some other examples. I don't want to go into details right now. These are available for you to see. This is a 3D stencil application and how we can improve the performance. The overlap between the user space and MPI is shown here in Vampire, the trace visualizer from TU Dresden. And you can then see the improvement in performance, optimized versus unoptimized, where there's more overlap now. And then you can see a plugin based architecture where we can change the threshold for eager to rendezvous protocol switch within an MPI operation. And then we can even have a plugin for auto tuning that can generate this, so it does it automatically for you. There are other scenarios for memory usage and message sizes where we can detect and then change this. The key takeaway over here is that Tau is a profiling tool that has many different measurement and instrumentation options, and it can work in concert with the MPI runtime. It can modify the values of the MPI runtime online based on the performance of the application. The auto-tuning plugin can work with the runtime. So there is an exchange of information between the tool and the runtime. And then you can also set many different options for generating different types of performance data. I will not go into details. This is just a quick listing of some of our options for memory debugging and control of the runtime. You can download Tau from this location, and also we have containers with Docker and Singularity from the Extreme Scale Scientific Software Stack or the E4S project. A lot of our development takes place in Eugene, Oregon, at the University of Oregon. We are now in Big Ten. And I would like to thank our sponsors from the Department of Energy, Department of Defense, National Science Foundation, NASA, our industry partners, CEA France, and our partners at other institutions, including the Ohio State University, the Paratools Inc., University of Tennessee, Knoxville, TU Dresden in Germany, and Jülich Supercomputing Center, the Exascale Computing Project, the Department of Energy Office of Science with the PESO project, and the STEP project. And I'll take any questions.
Let's give a thanks to Samir. Any questions for Samir? Yes.
Yes.
You can press that, Sadak. Yeah, so that remote people can hear.
Yeah, yeah.
Is better?
Yeah.
Okay. Yeah. So again, thank you for the talk, and it's really interesting. It's maybe more sort of a philosophical question. So you said there is a lot of complexity coming up.
There is a lot of
complexity from hardware coming up.
Yes,
makes things
exactly.
really difficult to measure. And then you did mention the containers and the other side. So because you work with such diverse teams, do you think people are trying to address that complexity, or they are just giving up and just taking it?
So, that's a very good question. The complexity often comes from the GPUs that are being integrated, and the need for performance portability is really important. And they are now looking at frameworks like Cocos and Raja to address that complexity so that they can write the code just once. And then internally, Cocos can spawn those kernels on the GPUs. Even if they lose some performance in doing that, they may be okay because they can maintain a code base that can be moved very easily from one architecture to another. So they trade off sometimes performance for that. And then our tools need to address the performance at the level of Cocos, at the level of the runtime, see what intranode and internode performance looks like, and then show it to them with as little information as possible, because tools are notorious for overwhelming the users with 30,000 functions that they can just drown in that data. So we do a lot to show you the views that I was showing earlier, which are timer calls inserted by application developers themselves in their frameworks that work with the MPI and Cocos to show you as little data as possible, but the data that will give you the most insights.
That is interesting. So yeah, it's kind of abstraction is changing both where you interface and what you share, because yeah, that's interesting. Coming from HPC, classic HPC background, you tend to had this feeling you had control, and now suddenly
Exactly.
don't. Thanks.
Thank you.
Any other question?
Or we can chat in the lunch. Thank
Yeah,
you.
okay. So with this, let's close the session again. Thanks, Samir. So with